Kinetics 3, Lecture 37, we're going to talk about the factors that affect the reaction rate, the activation energy, reaction mechanisms, and catalysis. Alright, so to start off, we've been talking about rates for the past 2 lessons, specifically about how to calculate the rate for a specific reactant or product and how to find the rate law. We talked about the integrated rate law as well as using the table method to find the rate law. So we have these rates. They tell us the speed at which the reaction occurs. We know some reactions are fast, some reactions are slow. We talked in the last lesson briefly about how temperature could change the rate or the speed of a reaction. But here we want to talk more in depth about what really affects the reaction rate. Why are some reactions so much faster than others? What is affecting that rate? So the first thing that affects the rate of a reaction is the rate of the collision between the reactants. So if the reactants collide a lot more often, then they're more likely to react than if they don't collide as much. Because in order for a reaction to occur, the 2 things or 3 things or 4 things, however many are involved in the reaction, must collide at some point. So how can we influence the rate at which they collide? Well, we can increase the concentration of our reactants, and that'll change how often they collide, right? If we have a lot more particles in the container in terms of concentration, then that will cause the rate of collision to increase. We can also mess with the temperature, because if we increase the temperature, the particles move faster, and if they move faster, they're probably going to collide more. Now, some things we don't necessarily have control over, but we can modify in some ways. For example, if something is a solid versus something that is a gas, those gas particles are obviously going to collide more than the solid particles, which are kind of locked in place. However, we can create a powder from a solid, and so that would give it more places where it could react. So that could change our rate of collision between the reactants. We could also dissolve a solid into water, and that would also allow more collisions to occur because those particles are going to move more than they would in the solid phase. So those are some ways that we can influence the collisions or the rate of the collisions. Another thing that affects the reaction rate is the percentage of collisions that have the correct orientation to produce a reaction. And really there's not much we can do about this. So when these particles collide, they have to collide aligned the correct way. And just by the nature of, I'm not sure the word I'm looking for, but percentages maybe, if something collides enough times, it's eventually going to collide so that it has the proper orientation. Okay, so if you throw a ball against a wall 7 times, it's eventually going to hit one side of the ball specifically. All right, so the same thing is true here. However, a catalyst will often hold one of the molecules in the right orientation, so then the other one just has to come by and hit it with the correct orientation. It's kind of like if you're trying to shake hands with someone and you reach out your right hand and they reach out their left hand, you can't shake hands with them. But if they reach out their right hand and you reach out your right hand, then a handshake could occur. The same thing is true with the reaction. We've got to have the 2 reactants turned the right way. So a catalyst can be useful because it can actually lock one of the reactants into the correct orientation, and that'll make it more likely that they will collide with the right orientation. The third thing that we need for a reaction to occur, so they have to collide with the right orientation, and then they have to collide with enough energy to produce a reaction. And that energy that they need is called the activation energy. So we can give molecules more energy by increasing the temperature. So as the temperature goes up, those particles are going to be moving faster. So they're going to have more energy, so it's more likely that they'll have enough to make the reaction occur. Another thing that we can do in terms of energy is, again, add a catalyst. And what a catalyst does is it decreases the energy requirement. So if less is required, then more likely they'll have enough if we decrease the requirement. But the temperature gives them more energy in general. So these are the three factors that affect reaction rate, and these are some ideas of how we could help a reaction along in terms of those three factors. All right, so here this is shown again. So the collision rate, all right, we said they have to collide. So how can we help them collide more often? We can mess with the concentration, and as it increases, it is going to increase the collision rate. We can change the surface area of reactants in the solid phase. So that would be grinding up a powder, for example. Grinding up a solid into a powder is going to help it react because there's more surface area. And also increasing the temperature will help us increase the collision rate. Remember, not every collision makes a chemical reaction, because not only do they have to collide, what are the next two factors? They have to collide with the right orientation, and they have to collide with enough energy. So not every collision makes a reaction. For example, if we want two of these NO2Cl molecules to react, there's a lot of different ways that they could collide. But the reaction only happens when they collide with the chlorines turned toward one another. If they collide in any other way, they're just going to bounce off of each other. No reaction. So you can see they can collide a lot of different ways, but only one collision is with the right orientation. And then lastly, they have to have enough energy. So this plot shows us, okay, here's our reactants. This is how much energy they have, potential energy. The more potential energy something has, the less stable it is. Okay, more potential energy, less stable. And then here's our products. So we can see the overall energy change from reactants to products. This is a good review. From reactants to products, we go down. So we know this is an exothermic reaction. Okay, just to review there. But in order for this reaction to occur, it has to get over this activation energy hump. So remember from our discussion of enthalpy, in order for a reaction to go, we have to break apart some of the bonds, and then we can start to make new bonds. So here in this activation energy, this is the activation energy when they're colliding and breaking bonds, and then when they start to make these new bonds. But we must have at least this much energy for the reaction to go. So if the two things collide, and let's say they have this much energy when they collide, up they go, but they can't make it over the hill. So they're just going to roll back down and turn back into reactants. They collide again, say they have this much energy. Up they go, they're on their way to becoming products, but nope, they don't have enough energy. So they roll back down. So when they collide, they have to collide in the right orientation, but then they have to have at least this much energy, if not more. So that's what you see over here. The energy of the collision has to be greater than or equal to that activation energy, or no reaction occurs. So there's a lot of requirements. It's like a miracle that any reaction occurs. They got to collide, then they've got to collide in the right orientation, and then they have to have enough energy. Right? If the energy of the collision is less than the activation energy, then the reaction is not going to happen, which is what I was showing you earlier. So it's going to go up the hill and turn around, go back down. No reaction occurs. However, if it has enough activation energy to get over the hump, then it will naturally roll back toward the products because they are at lower energy, and everything's trying to be at the lowest energy possible. All right, this should look familiar, hopefully. This is a Boltzmann distribution plot. So we have our kinetic energy along the x-axis and the number of molecules, or the fraction of those molecules, along the y. So we have 500 Kelvin and 1000 Kelvin. And remember, when you increase the temperature, it flattens out that plot because it spreads out those molecules more, because you've got more moving faster over here. And as it spreads out, this hump gets lower. Right? But it's actually moving faster because it's further to the right along the kinetic energy. If we plot our activation energy somewhere on here, let's say it's this amount, whatever this amount is, and we go up, just with a dotted line, any particles to the right of that point have enough energy to react. So you can see here on the purple plot, these particles have enough energy to react. So that is whatever that area right there is, that's the amount of particles we have at that temperature. However, if we increase the temperature to 1,000, now we have all of these particles to the right of the activation energy that are capable of reacting. So you can see with a doubling of our temperature, we get a lot more particles that are capable of reacting or have enough energy to react. Now we'll probably see this later, but just as a preview, if we come in and add a catalyst, what the catalyst is going to do is it's going to drop this activation energy requirement. So instead of being here, it's going to shift our activation energy back. And depending on how good of a catalyst it is, it'll shift it, however far. But even a small shift in activation energy, you can see will give us a lot more particles that are capable of reacting. All right, the activation energy for what we call a unimolecular, that's a single molecule decomposition reaction. Single molecule decomposition reaction. The energy required to break the bonds in the reactants is obtained during a collision with a background or a solvent particle. So what we're talking about here is, let's say you want to decompose ozone. Right? So to decompose ozone, you're making oxygen gas and a single oxygen atom. Well, decomposing ozone, nothing's colliding, right? It's just that one particle breaking apart. But we keep talking about these collisions that must occur. Well, the same thing is still true in a decomposition reaction. This M right here is not really involved in the reaction at all, and you can see that it would cancel out because it's on both sides. However, it's some background particle, so it could be something in the air with the ozone, or if the ozone's in water, it could be a water molecule. The collision of the ozone with that background molecule is actually what gives it enough energy to break the bonds and get over the activation energy hump. So even in a decomposition reaction where there's nothing else there, we still need collisions, and those collisions give us the energy to carry forth the decomposition reaction. For this reason, these decomposition reactions rates are going to increase as our temperature increases, because as the temperature goes up, these background molecules are moving faster. They're going to collide with that molecule we want to decompose more often and with more energy, and so that decomposition will happen more readily in those cases. All right, let's look at two energy diagrams again. So we have our reactants and our products. They're the same in both cases here. These are both exothermic. In the first one, we see there's a very large activation energy, and the second one, a much lower activation energy. So in general, when we have a large activation energy, it's going to be a slower reaction. But if it's lower, there's going to be more reactants that have enough energy to get over that hump, so we'll have a faster rate. Lower activation energy, faster rate. Higher activation energy, slower rate. So the rate really does depend on this activation energy. All right, so in summary, for a reaction to occur, we must collide. Two particles must collide. The collision has to have the correct orientation to yield a reaction, and the energy of that collision has to be greater than our activation energy. All right, so looking at activation energy again, here we see the forward and the reverse reactions in two different scenarios. So in an exothermic reaction, our product energy is less than our reactants because our products contain less potential energy. In an endothermic, our products contain more potential energy than our reactants. Okay, so it's just good review here. Exo, our products are lower. in potential energy, and then endo, our products are higher. So now let's think about what the activation energy has to do with endo and exo. So this one we're looking at first is exo. Okay, you see that on the left. The forward reaction has the activation energy that we see here. The reverse reaction, so all they did was they took this graph and flipped it around. So now we're looking at the reverse reaction. The reverse reaction, you can see it this way too, going back up this hill, has this activation energy. So the activation energy is different for the forward and reverse reactions. In this case, when it's exothermic, your forward has a lower activation energy than your reverse. So it's likely that your forward is going to be faster than your reverse in those cases. Alright, so we've been talking about the rates of reactions and all that has to occur for a reaction to occur. So in previous chapters we said that there were some reactions that were spontaneous and others that were not. But sometimes when a reaction is spontaneous or favorable, it still does not occur at any rate that we can measure. And when that happens, when we say, okay, our delta G is negative, our K value, our equilibrium constant value is greater than 1, everything seems favorable, yet the reaction is not going. What is wrong? We say that these reactions must be under what we call kinetic control. And this is often the result of a really high activation energy. So if a process does not proceed at a measurable rate, we can say, okay, it must have already reached equilibrium and it must be under kinetic control because of a high activation energy for either the forward or the reverse. So it's kind of stuck wherever it is because the activation energy to get to the other side is so high.